So our next talk is, we have our speaker, this is good. So, okay, so we have, our next talk is going to be Earthshine as an illumination source in the lunar permanently shadowed regions by Stubbs.
This is the right one, right?
Yes, is it working?
Yeah.
And I think the laser pointer might have been working.
Yeah, that looks good. All right, great.
Okay,
So I'm Tim Stubbs, but I'm actually really just a spokesperson for Dave Glennar, who couldn't make it. So the work I'm going to present has pretty much been led and pretty much mostly done by Dave. Okay, and this is an advance on some work that we presented here at the forum last year and is now very, very close to being submitted. So the two questions we're interested in is can Earthshine influence the stability of volatiles and PSRs? Can it be a significant player in that sort of heat balance equation? And so basically, the big question is, how does it compare to scattered sunlight? So that's the next big term. Okay, so then also in the absence of any scattered sunlight, is Earthshine bright enough for looking into craters? Optical sense and sight imaging, photometry, spectrometry, polarimetry, any of these things. Can you use it for that? So, example, if so during complete lunar night, when the pole was kind of looking towards the Earth, you're only getting Earthshine, no sunlight. Can you actually see anything in with that Earthshine? Okay, so this is the approach that we've taken. So we utilize the Virtual Planetary Laboratory, the VPL. Which is an Earth irradiance model in the form of spectral image cubes, and I'll show you some of those later on. They're very cool. So we kind of pick a test case. So for this, we take a very sort of simple crater, Shackleton-like crater geometry, and we stick it at the South Pole. And to try and sort of match it a little bit more with Shackleton, we tilt the plane by about 1.6 degrees. And so for some reason, Shackleton isn't exactly flat. It's kind of slightly shifted, and that makes a big difference when you're considering illumination. So this is the sort of crater shape we're adopting. So then we construct a shadowing code for the crater interior, and then we compute scattering using a Hapke rough surface reflectance function, and then we compute both direct and scattered irradiance of Earth and Sun within the crater. Okay, so here's a little cartoon of how we model that. So we kind of split between solar band, which is kind of shortward of 3 microns, and in that case, so here's the rim edge. There's the Earth. So we just kind of take the Earth irradiance and sort of just project onto a patch, and that's the only bit we consider because scattered Earth light for this calculation is pretty much negligible. So in the other case is the sun here hitting a patch, and you kind of illuminate a rim, and then that light then gets scattered from the rest of the crater, and we factor that in, and here's indicating that we kind of illuminate an Earth shadowed segment there. And then for the thermal case, similar sort of approach then, so we just get the Earth illumination on the patch here on this side of the rim, and so the sun's shining this direction, and then basically that thermal input is then kind of re-radiated, and you kind of get this thermal radiance sort of isotropically emitted from that surface to the rest of the crater, and that's our approach. Okay, so next up, it's kind of good to know what the Earth and the Sun look like when you're in the crater like this. And okay, and Dave's making the point here that the crater rim receives sunlight in summer only, so that's kind of when that becomes an important source. Okay, but so here we've got elevation angle. Here's the crater rim, and this is what the Earth looks like. So you can see the Earth gets pretty high in the sky, so that's a very important term. That light can kind of reach deeper into the crater, so that kind of makes it a big deal, potentially. And then, whoops, wrong one. And then you see the sun sort of oscillates here, so it follows this kind of annual trend, but then there's also this oscillation due to that 1.6 degree tilt of Shackleton that we factored in, which you can see can make quite a big difference. Okay, and just of course, and because the Earth is high in the sky, there's a greater fraction of the wall of the crater that can receive Earthshine. Okay, so then next we kind of look at the Earth irradiance at the moon, and this is the spectral component. So up here we have the solar band. And so this is shortward of 3 microns. And so this is the VPL, this gray line here. And so here we're showing, matching it up to epoxy measurements. And so, like I mentioned, that was an instrument that was repurposed on the Deep Impact mission to sort of then look at the Earth as if it were an exoplanet. And you can see that the VPR does a really great job, kind of matches up very nicely with the epoxy data, both in the visible channels and the IR. And Dave here has kind of taken the model here and kind of multiplied it by factor 10, so you can actually see some of the detail here in the spectra. And so you can kind of notice that there's some sort of big bite out. So obviously, anywhere we get some water lines, you get a lot of absorption there from the air spectra. And then sort of longward of 3 microns, we got the thermal component, which kind of is a natural split because pretty much the spectrum kind of drops out there due to the H2O absorption. And here we're comparing it to a MODTRAN model, which is an earth science model for upwelling of radiation. And again, VPR does a pretty nice job, and you can see there's some variation here due to sort of seasonal effects. And again, you can see some other absorption features like, again, H2O and a bunch of little absorption bands there, and CO2 and a few other things. So these are the very detailed spectra that we're using. But then if you actually look at an image of the Earth, obviously, the surface of the Earth is not homogeneous. So you have land, you have oceans, and that reflects sunlight in the solar band differently, and so that's what this patchiness is. That's just a different terrain, water, land, whatever. And of course, in the solar band, you have a phase, because obviously this is when you've got so near full illumination, but then obviously you're seeing the night side here. And when you're looking at the solar band at night, you don't get any reflected sunlight because the Earth doesn't see the sun there. And here Dave is kind of showing like the integrated sort of power sort of flux in milliwatts per meter squared that you get. So you can see it kind of goes from sort of near 50 milliwatts per meter squared, drops down to about 3 at night time. So this is definitely is highly variable. But then if you look down in the thermal band, you can see that you don't get really any variation with phase. It's very, very small. So you start off here at sort of 50 milliwatts per meter squared at full illumination, and only drops off by a few percent, and at night time it's about 43 milliwatts per meter squared. So this is essentially kind of almost constant all the time, and so on average this term actually is kind of a big deal. And if you kind of add these two together, you can see you're getting kind of between 50 and 100 milliwatts per meter squared, and that is not an insignificant flux term when you're thinking about PSRs. That's kind of bigger than the internal heat flow term you'd expect. Okay, so when you fold all these in, what does it look like? So here's the irradiance maps, and so Dave again is split up into solar band, and so the scattered solar light is about sort of 80 to 120 milliwatts per meter squared, and the Earth component is about 20, so it's kind of fairly minor. And if you kind of look here, so the sunlight is coming in from this direction, so the sun's over here, and you see there's kind of just that little kind of crescent there of illuminated rim, and that's kind of scattering light into the crater. And here you've kind of got this much sort of fatter crescent, and that's the Earthshine. And again, it's fatter because wider, because the Earth is higher in the sky. And then for the thermal term, so the rim irradiance is between sort of 500 and 800 milliwatts per meter squared, and the Earth is about 30 to 40, and so kind of this is a smaller fraction. And you see here you've got this illumination here, and again for the sunlight here, and then sort of scattering into the crater. And this is kind of the illumination pattern you get. But we should mention that that we've picked a case where the rim is very minimally sunlit, and obviously scattered light can get a lot bigger. So we're kind of sort of looking more towards the case where Earthshine could be important, which means that you want to look at a case where there's not much scattered sunlight. Okay, so next we switch to thinking of Earthshine as an illumination source, and so in this case we do consider scattered Earthshine and seeing if that's a big enough term to actually kind of light stuff up. And so we picked a case where you're not getting any scattered sunlight. The sun's completely below the horizon, and you're just kind of looking at the Earth. So this would be around sort of new moon, sort of looking towards the Earth. And so we picked this point A here, which is a point on the directly illuminated rim here, and you can see this is the irradiance, and it's pretty bright, and this is the upper radiance. So if you're flying over, this is what you'd be seeing. This is the light that would be coming upward. And then this point B in the middle of the crater is scattered light. You can see obviously it drops by about an order of magnitude 3 orders of magnitude down on the direct illumination, and here's the upper radiance you'd be seeing from that. And so the question is, could you image with either of these two? Well, so if you take the case of a very sensitive camera, and he's given some parameters in here, so like a resolution of 3 meters at 10 kilometers, sort of at around 450 nanometer wavelengths, and a spectral resolution of about 50 nanometers. So yeah, if you can integrate for long enough, sort of 100 seconds, then yeah, you can kind of get some signal to noises that are good enough to be able to maybe pull out some of the reflected Earthshine. But this is not a quite a tricky measurement. I think for example, I think UVS would probably be able to see the directly illuminated Earthshine pretty readily, but then it would be pretty tough to see the stuff the reflections from the reflected Earthshine in the middle here. Okay, thanks. So I guess you can kind of use Earthshine to look into craters, but it would be kind of tough. So you'd be able to see the rim, but it would be a struggle to see in the interior. Okay, so the conclusions are, so we've modeled the irradiance of Earthshine into Shackleton crater, the solar band and the thermal band. So we found that direct illumination by Earth contributes between about 50 and 100 milliwatts per meter squared, and so that's kind of many times what you'd expect from internal heat flow. So if you're not seeing any scattered sunlight, you're just seeing some Earthshine, then it becomes an important term compared to internal heat flow, which is probably somewhere around the 10 milliwatts per meter squared level. Okay. Again, it loses significance in the presence of any solar scattered sunlight, which typically dominates the input. And this risk recurs frequently in Shackleton because of that crater tilt. But obviously each PSR is different, so if you see something strange in a particular PSR, you kind of need to model that particular case to kind of really get a handle on it. So we kind of wanted just to sort of pick a typical case to show you kind of what kind of values you're dealing with. So the results show that direct Earth illumination provides adequate surface brightness for imaging or spectroscopy, but then with scattered Earthshine, it's far weaker, and detection to be detectable, it requires a some image intensification. All right, thank you.
We have time for questions.
Okay, actually, I've got a minute. I was going to say that we're probably going to take the same approach and look at Mars and Phobos, because in that case, Mars is much bigger in the sky of Phobos, and so that could be a much more significant term to heat balance at Phobos than maybe in the Earth-Moon case.
Okay, well, thank you very much.
Thanks.
Okay, let's see, we are